Alright, in this video we're going to be talking about section 4.3 that deals with the properties of logarithms. And in this section we're going to use three different rules: the product rule, the quotient rule, and the power rule. And we'll be using those to expand logarithmic expressions. Then we'll be condensing logarithmic expressions using the inverse of the three different rules: the product, the quotient, and the power rules. And then finally use the change of base property. Okay. So let's begin with the first rule, which is the product rule. Properties of exponents correspond to properties of logarithms. When we multiply powers of the same base, we always add the exponents. Like in this case here, b to the m times b to the n. Here we have, we're multiplying powers of the same base, so we bring over the base and just add the exponents. So for something like, let's say 3 to the 5th times 3 to the 7th. Here the bases are the same and we're multiplying, so we're going to bring over the 3 and then add 5 and 7 together to get 12. So we'll end up with 3 to the 12th power. That idea is used when we're dealing with properties of logarithms. Okay? So here, if I let b, m, and n be positive real numbers with b not equal to 1, this is our product rule. Log to the base b of m times n will be equal to log to the base b of m plus log to the base b of n. In other words, if I take the log of the product, that will be the sum of the individual logarithms. Okay? So the logarithm of a product will always be equivalent to the sum of their individual logarithms. So in this first example that we will look at, here we're going to use the product rule to expand each logarithmic expression, like log to the base 6 of 7 times 11. Notice that I do have the log of the product. I can write this as the sum of their individual logarithms. So log to the base 6 of 7 times 11, that's going to be equal to log to the base 6 of the first factor, which is 7, plus log to the base 6 of the second factor, which is 11. And that will be as far as I can go with that problem. So it will be log to the base 6 of 7 plus log to the base 6 of 11. Alright, the other example is log of 100 times x. And I did mention 100 times x because that is a product of 100 and x. So here we do have the log of the product. I can write that as the sum of their individual logarithms. So here I can write this as the log of the first factor, which is 100, plus the log of that variable, which is x. But I'm not done with that problem yet, because I can find out what log of 100 is. Okay? Now, if you want to, you can use your graphing calculator to find out what log of 100 is. Okay? So, if you remember the log key, which is right next to number 7 on the left side, you press that button and then type in the number 100 in close parentheses. That will tell you the log of 100 is 2. And that's basically because the log with the understood base of 10 means 10 to what power would give you 100, and that would have to be 2. So this will be 2 plus the log of x. Okay. So that's how we apply the product rule to expand that logarithmic expression. All right, next is the quotient rule. Now, here when we divide powers of the same base, we subtract our exponents. So that means if I have b to the m divided by b to the n, here the bases are the same, so I bring over the base and subtract the exponent in the numerator minus the exponent in the denominator, b to the m minus n. So if I had something like this, let's say 6 to the 9th divided by 6 to the 4th. Here, I'm dividing powers of the same base, so I bring over that base of 6, and then subtract 9 minus 4. And 9 minus 4 would give me 5, so I'll end up with 6 to the 5th as my answer. That idea is applicable to the quotient rule when you're dealing with logarithms. And in this case here, if I have log to the base b of m divided by n, that will be equal to log to the base b of m minus log to the base b of n. In other words, the log of the quotient, or the logarithm of the quotient, is going to be the difference of their individual logarithms. Okay. So, in example 2, we're going to apply the quotient rule to expand each logarithmic expression. Like in part A, log to the base 8 of 23 divided by x. Log to the base 8 of 23 divided by x. Here we got the log of the quotient. We got a numerator and a denominator that tells me we have a quotient and a log of the quotient. So I'm going to write that as the difference of the individual logarithms. So here, this would be log to the base 8 of the numerator, the numerator, that's 23, minus log to the base 8 of the denominator, which is x. And that will be as far as I can go with that problem. So this will end up being log to the base 8 of 23 minus log to the base 8 of x. And then part B, the natural logarithm of e to the 5th divided by 11. This also works if you have the natural logarithm as well. Here we can apply the quotient rule for this particular problem. So here, I do have a natural log of the quotient. I can write this as the difference of the individual natural logarithm. So this will expand to ln of e to the 5th minus ln of 11. But I'm not done with that problem yet, because I can apply one of the inverse properties of natural logarithms that I talked about in the last video. For ln of e to the 5, if you have the natural log of e to whatever your exponent is, it's going to be that exponent, because ln and e are inverses of each other. And I should write like this: ln of e to whatever your exponent is that exponent. So ln of e to the 5 is 5, and then minus ln of 11. And that will be the final answer right there. 5 minus ln of 11. All right, next we'll talk about the power rule. When an exponential expression is raised to a power, we multiply exponents. So b raised to the m times n, that would be this, b to the m times n. Here we're raising a power to a power. We bring over the base and multiply your exponents. So for something like 8 to the 5th raised to the 3rd power, we're raising a power to a power. So we bring over the base, which is 8, and then multiply 5 times 3. That's going to be 15. So that's applicable to the power rule for logarithms. Okay, in this case, if we have log to the base b of m raised to the power of p, that's going to be equivalent to p times log to the base b of m. So, in other words, the logarithm of a number with an exponent is the product of the exponent and the logarithm of that number. So what you're going to do there is pull the exponent in front of the logarithm. We'll just pull the exponent in front of the logarithm. So in example 3, here I want to use the power rule to expand each logarithmic expression. So here, if I have log to the base 6 of 3 to the 9th power, in this case, here my exponent is the 9, so I'm going to pull the exponent in front of that 9, in front of the logarithm. So that 9 will go in front. So it'd be 9 times log to the base 6 of 3. And that will be the final answer there. Now look at part B. You got the natural logarithm of the cube root of x. Now here, this doesn't have an exponent for us to put in front. That means I need to write the cube root of x in exponential form. There's a rule that says this. If I have the nth root of a to the power of m, I can write that in exponential form as this. Bring that base over, which is your a. The exponent for the a will be the numerator. The index, that's the number near the radical, that would be your denominator. So I can write the nth root of a to the m as a to the m over n power. So, for the cube root of x, I'm going to write that in exponential form. I'm going to bring the ln over. That x, I'll write that down. The exponent for the x is the understood 1. That 1 will be your numerator. This index of 3 will be your denominator. So, the cube root of x in exponential form will be x to the 1/3 power. So I get ln of x to the 1/3 power. And now I can go ahead and pull the 1/3 in front of the ln of x. So that 1/3 will be in front, and that'll be multiplied by ln of x. So the ln of the cube root of x will be 1/3 ln of x, using the power rule. And then part C, we got the log of the quantity x plus 4 squared. Well, my exponent is the 2, so I'm going to pull the 2 in front of the logarithm. So this will be the log, well, 2 times so here the 2 is in front. So it'll be 2 times the log of, and notice I'm keeping the x plus 4 in parentheses. If I left that parentheses out, it would be wrong because without the parentheses, I would be only taking the log of x and then multiply by 2 and add 4. So the x plus 4 is what I'm taking the log of, so that needs to be in parentheses. Okay, so the ones that we just did, we expanded logarithms using only one of the 3 different rules, either the product rule or the quotient rule or the power rule. Now, suppose we had a combination of all 3. And in some cases, you may need to expand using more than one property for logarithmic expressions. Okay, so this is just a summary of all three: the product rule, the quotient rule, and the power rule that I just got through talking about. Okay, now here's a study tip that I want you to be aware of. On the right side, you want to avoid those common errors here, like log to the base b of m plus n. That's not the same as taking the sum of the individual logarithms. Here, the log of the sum of m and n is not the same as the sum of their individual logarithms. The same thing holds true for the log of the difference of m and n. It's not the same as the difference of their individual logarithms. And log to the base b of m times n does not mean log to the base m times the log to the base b of n. So the log of the product is not the same as the product of their individual logarithms. Also, log to the base b of m divided by n. We can't say log to the base b of m divided by log to the base b of n. That's not what that means. And also log to the base b of m divided by log to the base b of m n is not this. And neither is this right here, log to the base b of m times n to the p. That does not mean you can pull this p in front. That p is for the exponent of n. So do avoid those. And here on the left side, they did a graphing. They used a graphing calculator to come up with the graph of ln of x plus 3 and ln of x plus ln of 3. Those two, you can see, are not the same. Okay? So use only the rules that I've given you right here. Now, let's look at example 4, part A. Here we're going to use the logarithmic properties to expand each expression as much as possible. Here we got log to the base b of x to the 4th times the cube root of y. Well, right off the top, I do have the log of the product, because that's x to the 4th times the cube root of y. Right off the top, I have the log of the product. I can write that as the sum of their individual logarithms. So here, I'm going to write this as log to the base b of x to the 4th plus log to the base b of the cube root of y. I'm going to write the cube root of y in its equivalent exponential form. So let me bring down log to the base b of x to the 4th, and then plus log to the base b of the cube root of y in its equivalent exponential form. Just like the cube root of x was x to the 1/3, the cube root of y would be y to the 1/3. Next step would be to use the power rule, because I do have exponents for each one of those. I can pull the exponent in front using the power rule. So for this term, I'll pull the 4 in front. So this will be 4 times log to the base b of x. And then plus, for log to the base b of y to the 1/3, I'll pull the 1/3 in front. So this will be 1/3 log to the base b of y. Okay. So that's part A. Okay. Now here's part B. Here we got the log to the base 5 of the square root of x divided by 25y cubed. And I want to expand this as far as I possibly can. So here, Notice I have a numerator and a denominator. That tells me I do have the log of the quotient, which I can expand as the difference of their individual logarithms. So I'm going to expand this as log to the base 5 of the numerator, which is a square root of x, minus log to the base 5 of the denominator, that's 25y cubed. Now in this case here, that square root of x, I'm going to write that in exponential form. So I'm going to bring down log to the base 5. The square root of x, I'm going to bring over the x. The exponent for the x is that understood 1. The index is a square root of x, so that's an understood 2 there. So that would be a 2 down here in the denominator. So the square root of x is x to the 1/2. So I have log to the base 5 of x to the 1/2. And then minus. Now, let's pay attention to this last term. Log to the base 5 of 25y cubed. Notice I have a log of the product, because this is 25 times y to the 3rd. I can expand this term using the product rule as the sum of their individual logarithms. So log to the base 5 of 25y cubed will be expanded as this. Log to the base 5 of the 25 plus log to the base 5 of y cubed. Okay. Now let's simplify this just a bit. Bring down the log to the base 5 of x to the 1/2 minus. Now, log to the base 5 of 25 I can simplify by finding out 5 to what power will give me 25. That will have to be 2, because 5 to the 2nd does give me 25. Now keep in mind, when you're finding the logarithm of some base to some number, you're trying to find out what the exponent is. So here, we're trying to find out 5 to what power will give me 25. That would be 2. And then plus log to the base 5 of y cubed. Okay, and notice that it is in parentheses, so this minus sign is going to change the sign of each and every term inside the parentheses to the opposite. So, here I'm just distributing the minus here, so I have log to the base 5 of x to the 1/2. Distribute that minus with the 2 will be minus 2. Distribute the minus with the plus log to the base 5 of y cubed will be minus log to the base 5 of y cubed. And that there will be the final answer to that particular problem. Okay. So when you're expanding logarithmic expressions, or more complicated logarithmic expressions, you first want to use the product and or the quotient rule wherever possible. And then second, use the power rule. Okay. So first you use the product rule and or the quotient rule wherever possible, and then second use the power rule to expand more complicated logarithmic expressions. Okay, so now the next thing we'll look at is the opposite of expanding a logarithmic expression, and that is to condense logarithmic expressions. To condense a logarithmic expression, we write the sum or difference of two or more logarithmic expressions as a single logarithmic expression. So, in this blue box, you do see the reverse order of that. So if you have the sum of their individual logarithms, we can condense that as the log of the product, as you see. The second one is if you have the difference of their individual logarithms. Here we can condense that as the log of the quotient, like this. And then finally, if you have a coefficient of your logarithm, that's p times log to the base b of m, that coefficient becomes the exponent for what's after the logarithm. We can condense that as log to the base b of m to the power of p. So we're doing the reverse of each of these three rules that I talked about. The reverse of the product rule, the reverse of the quotient rule, and the reverse of the power rule. And we're going to apply that to this example number 5. In this case here we got log of 25 plus the log of 4. And we're going to write that as a single logarithm. So here we got the sum of their individual logarithms. There you see the plus sign there. Excuse me. Here we got the sum of their individual logarithms. We can write that as the log of the product. So this will be the log of 25 times 4. But we can find out what 25 times 4 is. Just multiply those. So we have the log of 25 times 4, that's 100. Now we can find out what the log of 100 is. If you recall, we did this on the calculator by pressing the log key and then type in the number 100. That ended up being 2. So the log of 25 plus the log of 4 ends up as 2 as our final answer. Okay, part B. Here we got the log of the quantity 7x plus 6 minus log of x. Well, notice we have a minus sign in between the two logarithms. That means we do have the difference of their individual logarithms. So that means I can condense that as the log of the quotient using that quotient rule. So here I'm going to have the log of the 7x plus 6 will be the numerator. The denominator will be the x. So here you're going to end up with log of 7x plus 6 all divided by x as your final answer. Okay. All right, on the next page, here we're going to be dealing with more complicated expressions that we're going to have to condense. And it says here coefficients of logarithms must be a 1 before you can condense using the product and quotient rules. Very important. Your coefficients has to be a 1. So for this procedure, we're going to first use the power rule first. That way you'll have a coefficient of 1 for your logarithm, and then use the product and or the quotient rule wherever necessary. Okay. So now let's take a look at part A of example 6. It says here write as a single logarithm. In this case you got 2 ln of x plus 1/2 ln of the quantity x plus 5. And I want to condense that as a single logarithm. So here, this is what I need to do here. That 2 is the coefficient of ln of x. That 2 is going to be the exponent for the x in ln of x. So this will condense as ln of x squared. And then plus that 1/2 ln of the quantity x plus 5. That'd be ln of x plus 5, and that 1/2 would be the exponent for the x plus 5. So here I'm using the power rule first on each of those terms. And then next, notice I have a plus sign in between the two natural logarithms. So I do have the sum of their individual natural logarithms here. I can condense that using the product rule as this. Ln of, I'm going to put this in bracket, x squared times that x plus 5 raised to the 1/2. So here I'm condensing that using the product rule because of that plus sign. That tells me I need to condense that as the product of those two. Now that x plus 5 to the 1/2, I can write that in radical form. So this will be ln of, let's see, x squared, and then x plus 5 raised to the 1/2. That would be like the square root of x plus 5. And that would be as far as I would go with that problem. So here we have that as a single natural logarithm. Okay, next example, part B. Here we got 2 times the natural logarithm of x minus 3 minus the log of x. Well, notice the 2 in front of the log of x minus 3. That will have to be the exponent for x minus 3. Okay? And I'm doing that because I want that log to have a coefficient of 1, just like it did in the last example. So this will be the log of x minus 3, and that 2 will be your exponent for the x minus 3. So it'll be log of x minus 3 quantity squared. And then minus, there's nothing I can do with the log of x, so I'll just go ahead and bring that over. Now notice in this case I have a minus sign in between the two logarithms. So here I have the difference of the individual logarithms. I can write that using the quotient rule as the log of the quotient. So here, this will be the log of, and again I'll use brackets here, that x minus 3 quantity squared will be in the numerator. The x here will be in the denominator. So here I have, as my final answer, the log of x minus 3 quantity squared divided by x. So that is a single logarithm. And then part C. Now here, I got 1/4 log to the base b of x minus 2 log to the base b of 5 plus 10 log to the base b of y. So here I've got a combination of all 3 of these. So this is what I'm going to do here. I'm going to deal with this by using the power rule first. Make those logs have a coefficient of 1. So for that first term, 1/4 log to the base b of x. This 1/4 will be the exponent for x. So this will be log of, or log to the base b of x to the 1/4. And then minus, for 2 log to the base b of 5, this 2 will be the exponent for 5. So this will be log to the base b of 5 squared, and then minus this last term, 10 log to the base b of y. Well, that 10 would be the exponent for the y. So I'm going to have log to the base b of y to the 10th power. Okay. Now I'll be using the product and or the quotient rules here first, but let me give you a little hint on how to do something like this. If you have a plus sign in front of your logarithm, that will go in the numerator. If you have a minus sign in front of your logarithm, that term will go in the denominator. But make sure that your logarithms have a coefficient of 1 before you do this. Okay? So let me show you what I mean here. For log to the base b of x to the 1/4, Well, before I do that, I need to write log. Okay. And then write the vertical bar for the numerator and the denominator. Now, for log to the base b, can't forget that, log to the base b of x to the 1/4, there's a understood plus sign, so that means this x to the 1/4 will be in the numerator. Now for log to the base b of 5 squared, well, there's a minus sign in front of that, so 5 to the second goes in the denominator. And for log to the base b of y to the 10th, there's a minus sign in front of that as well, so y to the 10th will go in the denominator also. Now, I need to simplify this a bit. That x to the 1/4, I'm going to write that in radical form. So this means the 4 in the denominator, that's your index. The x would be to the 1. So I'll just leave it as the 4th root of x. Divided by 5 squared is 5 times 5. That's 25. And bring over your y to the 10th. So this will end up being log to the base b of the 4th root of x divided by 25 y to the 10th. And if you want to, let's put this in parentheses to show that we're taking the log of the entire quotient. Okay? So this technique is an easier way to condense that logarithmic expression. So here, if there's a plus sign in front of the logarithm, then what's after it goes in the numerator. And if there's a minus sign in front of the logarithm, then what's after the logarithm goes in the denominator. Okay. Last thing we'll look at in this section is the change of base property. This change of base property will help us find the logarithm or the natural logarithm of any number, regardless of what the base is. We can find a decimal value for that. Okay, so for any logarithmic bases a and b and any positive number m, log to the base b of m would be log to the base a of m divided by log to some base a of b. Okay, that right there is the general form here for the change of base property, which is this. But we're going to be dealing with these two right here, the common logarithms and natural logarithms. So for log to the base b of m, we can say log of m or log to the base 10 of m divided by log to the base 10 of b. That means log to the base 10 of whatever's after your logarithm, that's divided by log to the base 10 of b. That's going to be the subscript for your logarithm. Now also we can use natural logarithms here. And here they're using log to the base e. Yeah, log to the base e of m divided by log to the base b, e of b. Okay, so here it is right here to avoid all the confusion here. Log to the base b of m will be the log of m divided by the log of b if you're using common logarithms. Natural logarithms, you do ln. So it'll be log to the base b of m, which will be ln of m divided by ln of b. Now, you can use either one of these and you're still going to come up with the correct answer to your problem. Like in example 7, it says you use common logarithms to evaluate log to the base 7 of 2,506. So here's log to the base 7 of 2,506. So here we're going to be using this right here for common logarithms. the numerator will be the log of this number right here, 2,506, divided by the log of whatever the subscript is. That's 7. Now here, this is where we use our graphing calculator to find out what our answer is going to be. So here it is. You have to press the log key, which is right on the left side of the number 7 key, so LOG is there. Then we're going to type in 2,506 and close the parentheses because you only want the log of 2,506. That will be divided by, press the division key and then press the log key and then number 7, close parentheses. So your screen should look like this. And then finally press enter. And that will be the answer. Let's say I want to round that answer off to 3 decimal places here. So if I round it off to 3 decimal places, the third number after the decimal point is a 1. Next to it is a 9. That's bigger than 5, so that 1 will increase to a 2. So the log to the base 7 of 2,506 will be approximately 4.022. Okay. Now let's say in this example I want to use natural logarithms to evaluate log to the base 7 of 2,506. Same problem, but let's say I want to use natural logarithms here. So we're going to be using this right here, introducing natural logarithms using ln. So it'll be ln of this number 2,506 divided by ln of the subscript for the log, which is 7. So I get ln of 2,506 divided by ln of 7. So this time, instead of pressing the log key, I'll press the ln key, which is right below the log key on the left side. And then 2,506, close parentheses, divided by, then press the ln key again, 7, close parentheses. So you want to make sure 2,506 in this case is in parentheses and 7 is in parentheses as well. And then press your enter button to get your answer. You see you get the exact same answer here. Okay? So this will be approximately 4.022. There you go. So you can use either common logarithms or natural logarithms for your change of base property, and you're still going to get the same answer. Okay. All right, let me do one more of these, and that'll wrap up this particular video. Let's say you had something like this: log to the base 0.4 of, let's say, 11.2. And I want to solve this using a change of base property. Now I can use common logarithms if I want to, or I can use natural logarithms. Either way, I'll get the same answer. But in this case here, I'm going to use logarithms, common logarithms, which means this will be the log of this number 11.2 divided by the log of its subscript 0.4. So in this case, I'm going to press a log key of 11.2, close parentheses, divided by the log of 0.4, close parentheses. And then press enter. And I'm going to round this up to 3 decimal places here. So this will be negative 2.637. So here it came up with a negative value. So this will be negative 2.637. Now what that means here is this. If I take 0.04 to the negative 2.637, I will end up with approximately 11.2. Because when you're finding logarithms, you're dealing with, you're finding out what that exponent is. Okay. Alright, so this will complete this video on the properties of logarithms, section 4.3. That homework will be available for you to complete on My Math Lab, so make sure you have that completed. Also, please feel free to ask or email me any questions that you might have about the assignment or this particular lesson. Okay? So, thank you very much, and I'll talk to you next time.